Hi there. Welcome to Math A36, Calculus 2 for the Physical Sciences. Today we're going to talk about one of the nicest chapters in the theory of calculus, the theory of power series. So we're going to give an introduction to this topic. We're going to look at how we can use infinite polynomials to represent arbitrary functions by using the notion of series. It's really beautiful. It's a huge motivating part of the development of calculus. So let's get into it. What are our learning objectives for today? We're going to relate polynomials to their derivatives. Given a function f of x which has derivatives of all orders, we're going to write a Maclaurin series for f of x, and we're going to calculate the radius of convergence of a Maclaurin series. Our big motivating question for the day is going to be, what does the calculator do when you hit the e to the x button? So I remember getting this, this is a question I was curious about in high school. I remember saying, it's not multiplication, it's not addition, it's something else. What's going on there? And the answer, it turns out, is that it involves the theory of power series. So we're going to make some progress on answering that question. Let's get started. We're going to use a couple tools today. We're going to use the notion of the kth derivative, and we're going to write it in the following format. So we're going to write f with a k upstairs of x. So this is a way that we can write kth derivatives for any value of k. We're going to use the notation of k factorial, just k exclamation mark, and that's the product of all the numbers less than k. This exclamation mark makes us think, wow, that's really surprising. It's really huge. It's a very big number, k factorial. Previously, we've seen a test for infinite geometric series. So when does an infinite geometric series converge to 1 over 1 minus x? It converges when the absolute value of x is less than 1. Okay. And we're also going to use the ratio test. So a series converges if the limit of consecutive terms ak plus 1 over ak is less than 1. Okay, so these are some of the tools we're going to use today. We'll talk about kth derivatives, factorials, the infinite geometric series, as well as the ratio test. But those will come later in the talk. First, let's start off with something really down to earth. Let's start off with derivatives of polynomials. So how do we take the derivative of ax squared plus bx plus c? Well, let's get its first derivative. Okay, so we're going to say that this is f prime of x is 2ax plus b. And then its second derivative will be f prime prime of x 2, 1, a. Okay, now I'm writing this 1 here because it's going to be part of a general pattern that we're going to spot. But now that we have the derivatives, let's evaluate them at x equals 0. So this will give us f prime of 0 is b, and f prime prime of 0 is 2, 1, a. So check this out. This is a big step. This connection between the derivatives and the coefficients of our function. So notice that the b and the bx line up, this 2, 1a, and this ax squared line up. So the derivatives are keeping track of the coefficients of the polynomials. So there's this very nice connection between coefficients of polynomials and derivatives. Let's go a little bit deeper into this. So assume that we've got a whole number n and some big constant c. So we're thinking of n as something like 100 here. Which derivative of f of x is equal to cx to the n is non-zero when x equals 0? So take a moment, try and write something down, and then we'll go through the answer together. All right, let's check it out. So we've got our function f of x is cx to the n. Let's take its first derivative. Now we'll get cn x n minus 1. Our second derivative will be cn n minus 1 x n minus 2. And we can keep going like this. We can keep taking derivatives all the way until we get to the nth derivative. So that will be cn factorial, right? We'll take the product of all the values down to 1. And now let's see what we've got. Well, when we plug in x equals 0 here, this will 0 out. This will 0 out. This will 0 out as well. But this term here is going to be non-zero. Okay, so our correct answer is the nth derivative will be non-zero for this function. So what's very interesting here is that all higher derivatives will be 0. All lower derivatives will be 0. And we've got a function that has exactly one non-zero derivative. And that lets us build something very cool. So I'm going to call these designer functions. We're going to design a function to have specific properties that we want. So the function f of x is k divided by n factorial x to the n, has its nth derivative equal to k, and all of the other derivatives are 0 simultaneously. So we've chosen one value of one derivative and everything else is 0. Let's check out what that looks like. So we take this function, take its first derivative, we take its second derivative, and we can keep going in this manner until we get all the way to the nth derivative of this function. And then we get k n factorial, which cancels down to k. Okay, so when we plug in x equals to 0, we get k, and for all these other values, we're going to get 0. Okay, so everything is 0 except for the nth derivative, which is equal to k. So we've designed this function to have a very special property in its derivative. And we can put these things together to make functions with the properties that we want. So which polynomial has f of 0 is 1, its first derivative is 5, and its third derivative is 7? Take a moment, try and write something down, and then we'll go through the answer together. Let's take a look at it. So if we plug in 0, all of these terms will go away. So we have to have that a is 1. So we're going to get that a is 1. Now using this designer function, we're going to say that our first derivative should be 5. We don't know anything about the second derivative, except that it ought to be 0. Our third derivative should be 7. And our fourth derivative should be 0. Okay, so doing the arithmetic and simplifying, we get 1 plus 5x plus 7 sixths x cubed. And this function will have exactly the derivative properties that we've asked for. It's designed to do exactly what we're hoping it will do. So now the question is, could we do this at all orders in a polynomial? So suppose you want a function with specific derivatives. How would you go about building that function? Well, you could take our designer functions and add up a lot of them together. So let's have a look at that. An infinite sum of the following form, where we have the kth derivative divided by k factorial times x to the k. such an infinite sum will have exactly the derivatives that we want at each possible location. So we call such a thing a Maclaurin series. And they are sort of these infinite polynomials that have all the derivative properties that we want. Okay, let's have a look at one specific Maclaurin series. So we're going to look at the Maclaurin series of 1 over 1 minus x. And to do that, we first have to find all of the derivatives. So let's calculate the derivatives. So our first derivative will be f prime of x is negative 1 over 1 minus x, right? When we take the derivative of 1 over something, we get negative 1 over that thing squared. And we have a chain rule situation here where 1 minus x, we take the derivative of 1 minus x, and we get a negative 1. So we have 1 over 1 minus x squared. Now let's take our second derivative. So we're going to get negative 2, 1 minus x cubed. Again, we have a chain rule situation. So we multiply on a negative 1. And we get a 2 times 1, 1 minus x cubed. So again, I'm leaving this multiplication on top unsimplified so that I can spot a pattern that's emerging. Let's take our third derivative and see if we get a clear pattern. So we're going to get negative 3, 1 minus x to the 4 times 2 times 1 times negative 1. So we get 3, 2, 1, 1 minus x to the 4. Okay, now let's evaluate these things and see what we get at 0. So we'll plug in x equals 0 to each of these equations, and we'll see what we get. So this becomes f prime of 0 is 1. F prime prime of 0 is 2 times 1. And f triple prime of 0 is 3, 2, 1. So we can sort of notice a pattern here. What we're getting is a sequence of factorials. So we're going to say that the kth derivative at 0 is k factorial. Okay, so this is going to be very helpful in finding the Maclaurin series because we need the sequence of derivatives. So let's find the Maclaurin series. So we're going to get our derivatives from the last slide. So we notice the pattern that fk at 0 is k factorial. And now we will plug this into the Maclaurin formula. So the Maclaurin formula says that we should get g of x is the sum of the kth derivative at 0 divided by k factorial times x to the k. So we have the values of that kth derivative. And notice that those cancel out. The k factorials cancel out, and we're left looking at this. The sum of all of the powers of x. So we get 1 plus x squared, x cubed. So the Maclaurin series of 1 over 1 minus x is 1 plus x squared plus x cubed, and so on and so forth. We get an infinitely long series that represents the function 1 over 1 minus x. So we might ask, we have this series. When does it equal the function that we started off with? So when does 1 over 1 minus x actually equal out to 1 plus x squared plus x cubed, and so on? And also, what kind of series is this? So first off, let's identify the series. right? Have we seen anything like this before? So this is an infinite geometric series. With a common term x. So we're taking all of the powers of x. And we know something about the convergence of infinite geometric series. Okay, so we know that this is equal to 1 over 1 minus x when the absolute value of x is less than 1. Right? And this makes sense. If we were plugging in a number like x equals 10, we'd have 1 plus 10 plus 10 squared plus 10 cubed plus 10 to the 4, right? The function would very quickly diverge. But if we plug in a small number, then it winds up in something that converges. So we can rewrite this condition as x being in the interval -1 to 1. So that is the domain of this Maclaurin series. This is where the Maclaurin series makes sense or converges. So this is such a special region that we're going to give it a name. So this is called the radius of convergence of a Maclaurin series. It is the largest R such that the series converges for all x in -r to r. So we can say the Maclaurin series gx is x to the k has radius of convergence r equals 1, because the series converges for all values inside the interval -1 to 1. Okay, so now we've seen the infinite geometric series from the perspective of Maclaurin series. Now, let's go one step further and look at a transcendental function as a Maclaurin series. So now here's our big motivating question. What does the e to the x button do when you hit it? Right? What's this thing really doing? That e to the x and that ln button, what's really going on inside the calculator? So we're going to answer this using the theory of power series. Let's check it out. So we're going to find the Maclaurin series of f of x is e to the x. So our first step is going to be to get the derivatives of f of x. Okay, so our first derivative is going to be e to the x. Our second derivative is going to be e to the x. Wait, there's a pattern here. Our kth derivative is going to be e to the x as well. Okay, now we'll evaluate these. And when we evaluate, we get f prime of 0 is 1, f prime prime of 0 is 1, and all the way to the kth derivative is going to be 1. So now what we want to do is we want to use Taylor's formula. So now what we want to do is plug this into the Maclaurin formula. Okay, so we're going to get that g of x can be written as the sum of the kth derivative at 0 over k factorial x to the k. And substituting in that kth derivative, we get 1 over k factorial x to the k. Okay, beautiful power series representation of the function e to the x. Okay, so now we want to ask, what's the domain of this function? When is this function defined? So we're going to figure out when does the series converge. Okay, what values of x can we plug in that will make this converge? Well, from our previous slide, we have that g of x is the following. And this term here is the general term of our series, right? So these are our AKs. So what we have to do is we have to test when does the sum of these AKs converge. So to do that, we're going to apply the ratio test. Okay, so what do we need to calculate? We need to calculate the limit as n goes to infinity, an plus 1 over an. Now, in this case, this looks like 1 over n plus 1 factorial, x to the n plus 1, 1 over n factorial, x to the n. So notice that we have a lot of terms here that are common to the numerator and denominator. So this is going to be the limit as n goes to infinity. We'll cancel out the x to the n's. So we're going to get n factorial, n plus 1 factorial times x, which is the limit as n goes to infinity, x over n plus 1. And that will always be 0. So what we get is that this converges for all values of x. Okay, so we could say that this has an infinite radius of convergence. Every value in the real numbers causes this series to converge. Beautiful. Okay, so now we come to the big philosophical question of today's lecture. What does your calculator do when you hit e to the x? Well, calculators can add, they can multiply, so they can evaluate polynomials. And what it does is our calculator approximates e to the x as a polynomial with finitely many terms. Let's check this out. So we could take the first 4 terms of the Maclaurin series for e to the x. So we're going to take our whole infinite series, chop it off, and make a finite polynomial out of it. So let's check this. What happens when I plug in 0.36 into this? Well, my calculator gives the following answer, 1.43333294. Okay, so far so good. If we plug 0.36 into our polynomial, what do we get? We get 1.433. Okay, so we have 3 significant digits in common here. We've made some progress in approximating this. So in future lessons, we're going to look at questions like, how many terms do we need to take to get a good approximation? How quickly does this converge to e to the x? What is the error? This kind of thing. But for now, I just want you to keep in mind that the calculator is evaluating some finite polynomial, and it gets that polynomial from a power series. So thank you for participating. If you have any questions or comments, please check out the information below.